Just as we saw that a secant graph can be related to the graph of a corresponding cosine wave, a cosecant graph can be related to the graph of a corresponding sine wave. Recall that cosecant of x and sine of x have a reciprocal relationship. That is, cosecant of x is equal to 1 over sine of x. Therefore, if sine of x equals 0, then cosine of x is 1 over 0, or undefined. Just like we saw with secant and cosine, this means that everywhere that sine of x has an x-intercept, that is, the function value is 0, y equals cosecant of x will have a vertical asymptote. So observe on the graph, if we look at one fundamental cycle of sine of x, where sine of x has an x-intercept, cosecant of x has a corresponding vertical asymptote. Similarly, we can make the observation that if sine of x reaches its maximum or minimum value of plus or minus 1, then its reciprocal, cosecant of x, will share that value. So where sine of x is equal to 1 or negative 1, cosecant of x shares the same value. Also notice that as sine of x approaches its x-intercept, cosecant of x goes the opposite direction. So notice here, as sine of x approaches its x-intercept, cosecant of x goes the opposite direction, and that's true at this x-intercept as well. So the resulting cosecant graph looks like it bounces right off of that sine wave. It almost looks like a set of a couple of parabolas. Now, just like sine, cosecant has a period of 2 pi. We also want to write a formula for every possible asymptote across the entire domain of our cosecant wave. Notice the first vertical asymptote occurs at x equals 0. The next one is at x equals pi, and the next one is at the next multiple of 2 pi. Observing that pattern, we can see that the asymptotes are integer multiples of pi. So we say the asymptotes occur at x equals k pi, specifically for k in the integers. If we can locate those asymptotes, then we're going to exclude those values from the domain. So in set builder notation, the domain of cosecant is the set of all x such that x is not equal to k pi. And again, we're going to be clear and specify k can't be a fraction, it has to be an integer. The range, similar to secant, comes in 2 intervals. The lower half has y values from -infinity to -1, and we're going to unite that with the upper half with y values from 1 to infinity. So to graph a cosecant function, it is helpful if we graph a corresponding sine wave first. So let's try this on example 3. We want to graph one cycle of y equals negative cosecant of 2x. Now, before I do that, I'm going to think about its corresponding sine wave. So I'm going to graph negative sine of 2x, including the reflection across the x-axis and the change in the period. Because this is multiplied by a negative like our cosecant wave, we know that we're going to have to reflect the graph across the x-axis. So our sine wave, instead of having its ordinary roller coaster shape, is going to go the opposite direction. So we'll keep that in mind as we sketch the curve. Also notice that the period of this sine wave is 2 pi divided by the coefficient of the argument, 2, which is pi. So sine is going to complete one fundamental cycle in the interval between 0 and pi. So sine is going to be on the x-axis at the beginning and the ending of this period, and then halfway in between, it's going to cross the x-axis again. Now, before I go any further, I better label my scales. I'm going to use 2 tick marks per unit. Now we can complete our graph. Halfway between these two x-intercepts, sine is going to reach normally its maximum, but remember we're reflecting across the x-axis, so a minimum on this side and a maximum on this side. So we can sketch in one fundamental cycle of sine to get us started on cosecant. Now, the period of this cosecant function is going to be the same as the period we just discovered, 2 pi divided by the coefficient of the argument, or pi units. The asymptotes of this cosecant curve are going to occur everywhere that sine has an x-intercept. So notice we're going to get an asymptote at x equals 0, at x equals pi over 2, and x equals pi. And again, this is looking at one fundamental cycle of our cosecant curve. I'm going to go ahead and label those so we can see the pattern. Notice the distance between each asymptote is pi over 2. So the first asymptote occurs at 0, and then subsequent asymptotes occur at integer multiples of pi over 2. So we could say they occur at k pi over 2, where k represents an integer. So I can pick any integer value of k and plug it in there. It's going to generate a location of an asymptote. Now, once I get the asymptotes, the domain is easy. It's the set of all x such that x cannot equal the values generated by those asymptotes. K pi over 2, where k is an element of the integers. Now remember, the cosecant graph bounces off the graph of sine. So where sine has a value of -1, cosecant shares that value, but it proceeds in the opposite direction. So again, the green curve, the two little parabola shapes, are what compose the fundamental cycle of cosecant. Now, visualizing the range is going to go from -infinity to -1 for the lower half, and we'll unite this with the interval from 1 to infinity to describe the y values on the upper half. You're going to get practice graphing your sine waves, and you're also going to be able to use that to generate the graph of cosecant in this section. Let's try one more example. Graph one cycle of y equals 2 cosecant of 2x minus pi over 2. Notice the format of the argument. It is not in factored form. So in order to properly recognize phase shift, we do need to write that in factored form. So let's rewrite the function as 2 cosecant. I'm going to factor out the 2, and this leaves behind x minus, and just multiply by a half here, pi over 4. So our phase shift is pi over 4. Just to be sure, you can double check your factoring by redistributing. 2 times x gives you 2x. 2 times pi over 4 is 2 pi over 4, and that reduces to pi over 2. Now, to graph this cosecant function, we're going to think about the corresponding sine wave. That is, I want to think about y equals 2 sine of, and I'm going to write this in factored form, 2 times x minus pi over 4. So this graph has an amplitude change, it has a period change, and it has a phase shift. So we're looking at a lot of technical details here. Let's figure out the beginning and the end of one fundamental cycle of this sine wave. So the way I'm going to do that, as we always have done, is to take the argument and trap it between 0 and 2 pi. Okay, the reason we do that is because the argument, as the argument ranges between 0 and 2 pi, sine will go through all of its possible values. Solving for x, first by dividing all 3 parts by 2, we get 0 is less than or equal to x minus pi over 4, less than or equal to pi. Then we're going to add pi over 4 to all 3 parts. So we have pi over 4 is less than or equal to x, less than or equal to pi, plus pi over 4. So think 1 plus 1/4, 1 1/4, or 5 over 4. Or if you want to see the arithmetic here, we're going to get a common denominator of 4 and you can see we end up with 5 pi over 4. So the upper value for our fundamental cycle is 5 pi over 4. Let's add some specifics to the scale on the x-axis over here. Halfway between 0 and pi over 2, we have a multiple of pi over 4. So there's 1 pi over 4 to begin with. 2 pi over 4 reduces to pi over 2. This would be 3 pi over 4. 4 pi over 4 reduces to pi. And here is our 5 pi over 4. I'm also going to use 1 tick mark per unit for the scale on my y-axis. I think we're ready to sketch our sine wave. So the sine wave is going to begin its fundamental cycle at x equals pi over 4 on the x-axis. It's going to end its fundamental cycle at x equals 5 pi over 4 on the x-axis. Halfway in between, it's going to have another x-intercept. Now, halfway in between those first two x-intercepts, it's going to reach its maximum value with an amplitude of 2. And halfway in between the last two x-intercepts, it reaches its minimum value of -2. Remember, the amplitude changed to 2. Now, let's translate this information into the graph of cosecant. Everywhere that sine has an x-intercept, cosecant is going to have a vertical asymptote. So the first vertical asymptote here occurs at x equals pi over 4. Then the next one occurs at 3 pi over 4. And then finally, for this graph, the last one occurs at 5 pi over 4. Notice the distance between any two asymptotes is half of our period, or pi over 2. Now let's go ahead and construct our cosecant curve by bouncing it off of the sine wave. So it's going to share the maximum and minimum value of sine. It's going to bounce off the sine wave, as I like to say, and extend in the opposite direction. Let's list the specifics of this curve. First of all, the period is the original period of cosecant divided by the coefficient of the argument, which is 2. So the period of our cosecant curve is pi. Notice that the distance between pi over 4 and 5 pi over 4 is pi. The difference there is 4 pi over 4, or pi. Now there's a couple of ways that we can express the asymptotes. One is simply to start at the location of the first asymptote, which is at pi over 4, and then recognize that we can add any multiple of pi over 2, where k is an integer, to land at the next one. So if I start at pi over 4, I add pi over 2, or another multiple of pi over 2, that's going to continuously generate each asymptote. Or if you notice in the pattern of the asymptotes that we wrote up here, they are all odd multiples of pi over 4. So another way to express this location would be to indicate that we're dealing with odd multiples of pi over 4. Now, how do I write an odd number in the form of a formula? Well, if k is an integer, then 2k is an even integer, right? If you take any integer and multiply it by 2, it's going to be even. Well, if you add 1 to that even number, you're going to get an odd number. So the way to write an odd number in code is 2k plus 1. So 2k plus 1 pi over 4 gives me the formula for every possible asymptote, but we have to specify that k is an integer. Now, just to help you understand this from every perspective, another way to see that these are equivalent is to start with this one, pi over 4 plus k pi over 2, and add them together with a common denominator. If I get a denominator of 4 for that second fraction, I've multiplied the denominator by 2, so I need to multiply the numerator by 2. Then notice we could factor out a pi from those two fractions. As we combine the numerators, we'd end up with 2k plus 1 pi over 4. So any way you think about it, whatever relationship makes the most sense, the most important thing is that you are recognizing those relationships. And don't worry, it does take a little bit of practice. For the domain, once we've found the asymptotes, the domain is easy to express. It's the set of all x such that x cannot equal those asymptotes. I'm going to write it as 2k plus 1 pi over 4, where k is an integer. And finally, the range. We're going to range from negative infinity to negative 2 and unite that with the interval from 2 to infinity. So the key to graphing both a secant and a cosecant is to first graph the corresponding sine or cosine, and understanding the appropriate reciprocal relationship, then cosecant or secant will bounce off of the corresponding sine or cosine wave. And don't forget, you can certainly check this with your calculator.